Let me give you one more example of a set of vectors that are linearly dependent. And actually, I just discovered this by accident, making up a quiz one day for 319. I didn't actually realize this before I gave the quiz. I thought, well, what's an interesting matrix? Let's consider this matrix right here, this 3 by 3 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. I thought, well, that's kind of an interesting matrix. You know, it just follows that pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9. And consider these 3 vectors, column vectors. V1 equals 1, 4, 7. First column. V2 equals 2, 5, 8. And V3 equals 3, 6, 9. Now these 3 vectors are linearly dependent if and only if, giving our latest definition of this, you could write K1 V1 plus K2 V2 plus K3 V3 equals 0. And you can find values for K1, K2, and K3 that make this true. And all the K1, K2, K3 are not all 0. Does anybody see what values for K1, K2, and K3 will work? Okay, let's see. Johnny, what are you making V1? Oh, yes, thank you. Not V1, K1. We know what V1 is. 7. What about K2? -2. What about K3? Let's see if that works. What would 7V1 be? 7V1 would be 7, 28, and 7 sevens are 49, right? K2 minus 2 V2 would be minus 4, minus 10, minus 16. And then minus 1, K3, would just put a minus in front of that V3. It would be minus 3, minus 6, minus 9. Now add those up, and what do we get? Well, the first one works, doesn't it? Oh, no, I don't think the second one works, does it? 28 minus 10 minus 6. It doesn't look like it works for the first one, but it doesn't work for the second one. It doesn't look like it works for the third one either. But at least the first one worked, Johnny. I think there are simpler numbers than that'll work. What's that? -5 for K1. And what for K2, Andrew? 1. And what for K3? -1. Okay, let's see if that works. Minus 5 V1 is going to be minus 5 minus 20 and minus 35. And then 1 times V2 is 258. Okay. And then minus would be just the same as before. Positive 1 for K3? Okay. All right, so this would be.
Why don't we solve it instead of saying a guessing game?
Okay. What I'm going to do, I promise this is the last time I'll do this. And then I'll show you, Jonna, an actual neater trick so you don't have to do this. Okay. All right. So does this work? I don't think this works either, does it? Because the minus 20, 5, and 6, that won't work there. Okay. All right. Okay. Well, Johnny, your point is a good one. Let me just tell you there are values of K1, K2, and K3 that satisfy this, and I'll let you work on it. And then next class, I'll show you a neat trick that you can use to determine whether or not a set of vectors is linear dependent or independent. Now, the question is, are these 3 column vectors linearly dependent, or are they linearly independent? Okay. We stated the theorem in class on Friday that if you could write K1V1 plus K2V2 plus K3V3 equal to 0. And by 0 here, I mean the 3 by 1 vector of zeros. That these 3 vectors are linearly dependent. If you can find values of K1, K2, K3 that make this true. For K1, K2, K3, not all 0. Okay. And has anybody found values for K1, K2, K3 for these 3 scalars that'll make this true? Somebody found them, some values. Anybody? Get a bonus point if you add it to your quiz, if you can find values for K1, K2, K3 that'll make that true. What's that? Anybody? I thought somebody after class. Andrew? Let's try K1 equal negative 1. Yes. K2 equals 2. K3 equals what?
1.
Is it 1? Negative 1. Okay. And that'll work because if you take 2 times V2, notice you get 4. Well, let me go back. Let me just write it out. Minus 1 times V1 is this. Plus 2 times V2 is this. Minus 1 times V3 equals the 3 by 1 vector 0, 0, 0. Okay. As you could see, minus 1 times that gives you minus 1 plus 4 minus 3. That gives you a 0 here. Looking at the second row, we get minus 4 plus 10. That will be a 6. Minus 6 equals 0. And then finally for this bottom row, minus 7 plus 16 would be 9 minus 9, 0. Very good. Andrew, you bring up your quiz after class. I'll give you extra point on your quiz for that. Okay. Therefore, since we found non-zero values for these three scalars, that'll make that statement true. Therefore, these column vectors are linearly dependent. Okay. Well, now, why is this important? The reason it's important is because if the column vectors or the row vectors, either one, if the column vectors or row vectors are linearly dependent, then there won't exist a unique solution to the equation system with that coefficient matrix. Okay. Now, you can't just look at expressions like this and easily find the scalars, as Andrew did. It took a while to figure that out. And sometimes the scalars might not even be whole numbers. So it's going to be tricky to figure out what those scalar values are.